Hi everyone, my name is Perry, and today I will be presenting our paper named Self-Supervised Material and Texture Representation Learning for Remote Sensing Tasks. Remote sensing data is used for many essential applications such as natural disaster damage assessment, urban planning and mapping, climate change tracking, population migration, and more. However, most of those tasks require expensive annotations that require specific domain expertise. We have many unannotated remote sensing data which are expensive to annotate. So for example, for this image from the change detection dataset, it would be difficult to immediately find this change. So here we look to find a way to use that data without the annotation requirement in a self-supervised way. In this work, we look at material and texture representation learning. And now, why is material and texture representation important? Say we can describe material and texture. That means that we can also describe most or all semantic classes. So vegetation representation may be related to the semantic classes of grass, forest, or football field, while soil representation may be related to the semantic classes of forest or construction site. And unlike typical self-supervised methods, here we learn local descriptors based on a material and texture approach. So we get pixel-wise surface features and not global for the entire image. Generally speaking, material and texture representation depend on low-level features like edges, material signatures, and spatial patterns. That means that any deep network would remove most impact of those features given their large receptive fields aimed to learn higher level features. So we have two contradicting objectives here. On one hand, material and texture learning depend on low-level features, which diminish in deep networks. On the other hand, we need deep networks which have large learning capacity for downstream tasks. And classical and other methods don't really solve this problem. So classical methods like textons are fragile and overly sensitive to small texture and material irregularities, while deep learning approaches are overly generalizing surfaces, which causes overgrouping. So let me take a step back and explain our initial assumptions and overall pipeline. Given a multitemporal and specially aligned pair of images, we enforce feature similarity on the unchanged regions. The temporally consecutive patches give us a naturally occurring data augmentation that is caused by the changes of illumination direction and viewing angle. We then can enforce similarity of those patches to essentially learn invariance to illumination and viewing angles. So as mentioned before, we want to increase the impact of low-level features in the pre-training portions, and we do it in two ways. One, we define no-go regions by using patch-wise inputs, and second, we refine low-level features based on interkernel similarity and variance. And those two allow us to implicitly decrease the receptive field of the network without reducing the learning capacity of the network, a learning capacity which is important for our downstream tasks. Generally, self-supervision is another way of defining a clustering problem. In classification, self-supervised methods cluster class instances and encourage latent features similarity to other images within the same class. Here, we may have ambiguous data inputs due to their sampling. Given a patch, it is likely that it may belong to multiple materials and textures, say if it is an over soil and vegetation mixture. So we address it by using residuals as a measurement of affinity between a given input patch and all learned clusters. So patch-wise inputs give explicit receptive field constraint. Then we have our texture refinement, which to amplify low-level features based on texture. And lastly, we have residuals, which handles fragility by allowing concise representation of patches that contain multiple material and textures. So in this slide, we present the results on the change detection task. We show that the results of our model without any usage of labels, simply by looking at the difference of residuals of two consecutive frames, we can detect local change of material and texture between two images to determine the overall change. As you can see, our unsupervised method outperforms the fine-tuned method of the current state-of-the-art presented in ICCV 2021 in purple. Then we also show that our method gets even better results when fine-tuned with labels. Additionally, due to the effective pre-training in material and texture representation, fine-tuning our methods on other downstream tasks converges 76% faster and provides better performance overall. Thank you, everyone.